Alright guys, I put together a little worksheet that hopefully will help answer the questions like, should I be able to do this? So it just says you should be able to and then I've got a bunch of things filled in. So we'll go, there's bullet points, we'll kind of go off the bullet points here. Yeah.
Because like
I don't think it's as bad as the last one. This one's all applications. And I think that question always depends on how hard you find the material. Because there's never going to be one test that's like, oh, everybody thinks it's super hard or everybody thinks it's super easy.
which version did I have?
Alright guys, so everyone should have one of these. We're going to go through kind of the different bullet points. One of the things that I definitely want to make is that graph theory chart, like the F double prime, F prime chart, because that's going to help you with a lot of things. And I would even maybe, like I had people that did this all the time last year. When you get the test, just kind of like regurgitate that table onto the test, and then you can reference. Everyone, what it like brain dump, like people have all sorts of gross ways to refer to like just writing all of the things that you have in your head. And that brain dump is really gross. Regurgitate is also gross.
I do brain dump.
Brain dump? Just like,
Oh, I totally brain dump.
just throw all sorts of things that you have.
Yeah, for anatomy, I just write like the 4 things that I memorized.
Yep.
And then I just
So that chart, the F prime, F double prime chart would be a great thing to just put on your test. Okay, so we're going to go through kind of bullet by bullet and talk about how to do these things. And then the F prime, F double prime chart will cover a lot of these things. Okay, so starting with critical points. Okay, so finding critical points, bullet point number 1. We did this kind of right away in 4.2. So how do we find critical points?
Just derivative equals 0.
Okay, set the derivative equal to 0. So we take F prime, set it equal to 0. Or what's the part we forget about? Also when the derivative doesn't exist or is undefined. Is D and E okay for doesn't exist? You guys good with that? Okay, so derivative either equals 0 or does not exist. Polynomials you don't have to worry about. Polynomials will always exist. But if you have like rationals, like trig, you know, something like that, make sure you check, bless you, make sure you check for where it does not exist. Next, absolute extrema. That was also from 4.2. Absolute extrema is when you're given a closed interval. So that one, do you guys remember that stupid like hand thing that I had you guys do? Endpoints, critical points. So those are 2 things that you're looking for. So if you're looking for absolute maxes or absolute mins, check the endpoints, check the critical points. So absolute extrema. So there are a lot of different problems where you have to start by finding the critical points. So do yourself a favor and know how to do that. And finding the critical points means taking the derivative, which means you are responsible for any derivative rules that you have back in your little memory bank somewhere. So anything from chapter 3, you're still responsible for any of those derivatives. Any of the basic ones, product, quotient, chain, things like that. So absolute extrema, you are going to plug your critical points and endpoints into what? What do you plug those points into?
Original.
The original function. Good. So those are going into the original f of x. Make a table out of it. Pick which one's the highest, which one's the lowest. Question?
Endpoints are usually like give to us, right?
Endpoints are always given, yes. So they'll say like what is the absolute max of f of x. They'll give you a function and they'll say on the interval like -2 to 5 or whatever. So yeah, on a closed interval, those endpoints are just handed right to you. Okay, so plug critical points and endpoints into your function, and then you're literally just picking like, oh, this is the highest y value, this is the lowest y value, you identify those. And when they ask for maximum and minimum values, it's the y value that they want, unless the question is phrased like, at which x value does the absolute maximum occur, then they want the x value, but usually max and minimum values mean y. Okay, good on that?
Yes.
Okay. Next, the mean value theorem. Okay, so mean value theorem, I will write the statement of that out. Do you guys remember the opening hypotheses, like what has to be true before you even dive into the mean value theorem? Differentiable and continuous. Good, so the function we're starting off with, f of x is differentiable and continuous. So really we could say it's differentiable. You guys remember that? Being differentiable, it has to be continuous. Okay, so if you get a mean value theorem problem, start with that. Like start with just a statement. Like, oh, I know that this function is continuous and differentiable. If it's a polynomial, that's easy. If it's like a rational, make sure that it's continuous on the interval, things like that. If I'm asking you to use the mean value theorem, I'm not tricking you. Like it will be differentiable and continuous. So just make sure you start with that statement so you know you can even use the theorem. Okay, so theorem looks like this. There is an x value that we'll call c on the interval a to b, and they will always give you the interval. This interval will always be given to you in the problem. So there is an x value c on a to b such that, and basically what it means is that the derivative at a point is equal to the average rate of change, or the slope. Okay, so the function has to be differentiable and continuous. You just state that. And then it says you're going to be able to find some point on a to b. So the question will say something like, verify the mean value theorem for this function on this interval. You'll do this first. Do the average rate of change. Again, a and b will be given to you. So set up the average rate of change. Let's say it comes out to be like 2. Then what you do is you set the derivative equal to 2 and show that you come up with an answer. And you got to make sure, like, say you come up with multiple answers, you only count the ones that fall on the interval. Okay, so does that make sense what you guys would do with that question? Mm-hmm. If it had a natural log in it, to get rid of the natural log, you'd have to raise it as a power on e. But if we have, once I get through these bullet points, if you want to pull that specific example, we can go through it. Okay, the next stuff that we have, so increasing, decreasing, concavity, max and min, inflection points. For kind of all of these bullet points, I'm just going to set up that graph theory chart. So this is something, like, if you get one thing out of this review, this chart should hopefully be it, because this will help you with a whole bunch of stuff. So it's called graph theory. I told you guys a couple times. Remember, it accounts for somewhere around 25–30% of the AP test. How f relates to f prime, how it relates to f double prime. Okay, so let's see how much of this you guys remember. So down the F column, there are 7 things that we want here. What features of F do we care about? Increasing, decreasing. What kind of pairs with those?
Concave up and concave down.
That kind of goes into a different category. What else stays along the lines of increasing, decreasing? Max, min, good. Good. Oops. Min. Yeah, so these are technically the relative or the local max and mins. Absolute, we already know how those are found. We've got a different technique. So max, min. Okay, so then Renee, what else did you say?
Concave up.
Concave up and concave down. And then what kind of goes with concavity? The last thing.
Pips, IPs.
Good, inflection points. Good, so we say potential inflection points, or just when we're setting the second derivative equal to 0? This is actually like confirmed inflection points once we check for a sign change. Okay, so we are going to go down the F prime column first, because F prime is the most useful one that we can see. And if you guys look at right about here on this worksheet I gave you, it's somewhere right around the middle, a little past the middle. It's the only one that has 2 lines. Use a graph of F prime to identify where F is increasing, decreasing. So I'm not even being subtle about this. Like, I am directly telling you there will be a graph of F prime on the test, and you will have to answer all these questions. Okay, and you will have to write AP-worthy explanations and interpretations. So you'll have to say, you know, F is increasing on this interval because F prime is positive there. Like giving all those. So you will have F prime in front of you, which means memorizing this chart and just spitting it out on your test would be a really great idea. So all these things are super important. So if F is increasing, F prime is positive. Decreasing? Negative. Okay, how about a max? Positive to negative. Good. So our first derivative has a sign change, specifically positive to negative. And then min would be negative to positive. Okay, so now these ones are a little bit trickier to get from f prime. If f is concave up, what is f prime doing? Increasing. Good. That's actually the first definition that I gave you guys of concavity. If it's concave up, that means the slopes are increasing the whole time. All right, and so if f is concave down, the slopes are decreasing. We'll translate this to f double prime in just a minute. And then how about inflection points? We're in like the right area. Maxes and mins. Good. Okay, so maxes and mins of f prime. And it doesn't matter, the max or the min. Because remember, maxes and mins, we actually define a certain sign change. Inflection points, it's just any sign change. So it doesn't matter if it's a max or min. So this would be either f prime changing from increasing to decreasing or decreasing to increasing. So you could also consider this to be like a change in direction. So if f prime changes direction, again, meaning increasing to decreasing or decreasing to increasing. Okay, so that is everything that f prime will tell you. That middle column is super, super, super important because like I said, you will have a graph of f prime in front of you and be asked a whole bunch of questions about f. Okay, so now f double prime doesn't tell us anything about these first four. F prime just comes into play here. So if f is concave up, f double prime is positive. And notice that these two columns have the exact same relationship that these two columns have. Because this is the original and this is the derivative, we can also view this is the original and this is the derivative. So all of these relationships should be the same as these relationships. Which means if f prime is decreasing, if f is concave down, that means f double prime is negative. And then if f has an inflection point, what will you see in f double prime? Change in, not direction, but sign. Either sign change. Like I said, we don't give a specific name. Doesn't matter if it's positive to negative or negative to positive. So that like this relationship matches up with these two right here. So no specific name given. So this is super, super important. 7 rows, have them memorize. It'll give you a lot of information. Okay, so that's your graph theory chart. That covers a bunch of the bullet points. There are a couple things left. I want to cover the 2 tests for relative extrema, the first derivative test and the second derivative test for relative extrema. So go there next. So we've got 2 tests for relative extrema. Question?
What sections was the graph theory chart?
A little bit of everything, 4.2, 4.3, and 4.4. Kind of combines everything because we had the critical point stuff in 4.2. We had the increasing, decreasing, max, min stuff in 4.3, and then concavity stuff in 4.4. Okay. So, little blend. All right, so test for relative extrema. So basically what these tests are doing, either first or second derivative test, is we use these tests to determine whether a critical point is max, min, or neither. Okay, so we've got 2 options for this. First derivative test, I think you guys have done a lot more work with. Second derivative test, we spent some time on. I definitely want to recap it because it's convenient in certain situations. So I'll explain one. So first derivative test. So let's start with this. Let's say we've got a critical point, call it x equals a. So this doesn't mean we don't have more. Like we probably have multiple critical points. I'm just going to focus on one. So this is how we can use the first derivative to tell us whether x equals a is a max, min, or neither. What's the main focus, the main feature of the first derivative test? What do we use for first derivative tests? Oh, come on. How do we use the first derivative to tell us whether whether a critical point is max, min, or neither? Sign charts. Yeah, so we're going to set up a little sign chart. They're always f prime sign charts. And we're going to use a sign change to tell us whether A is a max, min, or neither. So looking for a sign change here, how many possible sign changes do I have?
1, 2, 1. One change, 2 different signs. Yes. You could have 1 change.
Okay, so 2 different signs. So I'm sorry, I guess I should say what are all the possible sign combinations?
Get 4.
4. There are 4 possible sign combinations. Okay, so 4 possible sign graphs that we have. I apologize, I phrased that strangely. So 4 sign combinations that could happen at A. Maybe a change, maybe not. Okay, what's one? Positive, positive. Negative, negative. Positive, negative. Negative, positive. Okay, so those are all 4 things that could happen at x equals A.
Charlie just did that in his sleep.
He said Charlie just did that in his sleep. All right, so positive, positive, what does that mean for x equals A? It's neither. Good, so this would be neither max nor min, because yeah, we stop for a second, but there's no change in sign. So that would be like the chair graph that kind of increases, stops, and then increases again. How about negative, negative? That would again be neither, no sign change. So that would just be like a backward sign chair, decreasing, levels off for a minute, and then keeps decreasing. Positive, negative change would be a max. And negative, positive, min. Okay, so 2 different ways to be neither. And then we've got the max or min. So 4 possible sign combinations to the left and to the right of A. Okay, so that's what the first derivative test tells us. You guys good with that? Okay, so let's look at the second. Again, less experience with this, so we'll recap it right now. So second derivative test is literally just based on the sign of the second derivative at that point. So second derivative test, the same setup. Let's say we've got one particular critical point that we'll just call A. And so what you do at that critical point is we have the second derivative. So this one is kind of 2 options. If for some reason you already had the second derivative, like if you needed it for a different part of the problem, you might as well do the second derivative test. Or let's say that your function was like super, super easy. Like if it was a polynomial, you might as well just take the second derivative. Because taking the second derivative is just as easy as taking the first. If you have like a quotient, like a chain rule, like something where taking the second derivative would be a little bit painful, don't. You guys will have one, well, I will just tell you, like use the second derivative test to find these critical points. So you will be using it tomorrow. All right, so here are your options. We take A, we're just going to plug it into F double prime. So how many different outcomes could there be? If we plug in A, how many different outcomes could there be?
4.
Not 4. How many? Not 2. Not 1. 3. Really good guessing, guys. What are the 3 outcomes that you could have? Greater than 0, less than 0, equal to 0. We just kind of played process of elimination right there, guys, but we got there. We got to 3. Okay, so those are your 3 different options. Remember, this is the rule that's kind of counterintuitive. So if you plug A in and you come up with a positive value for the second derivative, what does that tell you about F? If the second derivative is positive, what does that tell you about F? It's concave up. So if it's concave up, A would be a min. Good, because remember, looks like that. Okay, so this would actually be a min. Counterintuitive. Power or positive doesn't seem like it should match up with min, but it does. Just picture the graph. You guys did this in algebra. Do you guys remember doing this in algebra with parabolas? Like you'd look at the a in front of the x squared and say like, oh, it's negative, so my parabola must be upside down, and that means the vertex is a maximum. I know you did it because I'm doing it with my college algebra kids right now. So this one, okay, so if your second derivative comes out negative, that means f is concave down, so it looks like that, which means your critical point would be a max. Okay, and then the next one, if f double prime is equal to 0, something weird is happening there. There's like a change in concavity. And normally if there's a change in concavity, there isn't going to be a change in sign. There would have to be some sort of very strange scenario happening, because if concavity is changing, normally sign is not changing, because otherwise you would have some sort of weird non-differentiable situation. So it could happen that you do have a max or min, but for anything that we have seen, this is what turns out to be neither. What the test technically says that you guys have in your notes is test is inconclusive. And then the notes tell you to go back and do the first derivative test. I can tell you that I have never seen it. Oh, giraffes. Are you serious? I can't.
Swear word, like, oh, giraffe.
Oh my God. Come on, giraffes. Get off of my screen.
Funny.
Anyone that's watching that's on the Latin trip is probably very confused because their screen still looks exactly the same. No, okay. Nope, the giraffes are here. Come on. They'll understand. They know when the giraffes are here. 105. Oh my gosh.
Looking at the giraffes.
There we go. Okay. We're back. I think we should start using giraffes as a swear word. Like, it's something that we should consider. Okay. Okay, so anyway, we got our second derivative test. Okay, are you guys good?
I'm crying. I love the giraffe.
First I was suggested we name them, and I said you guys already did, but I couldn't remember.
We didn't come up like with a for sure name. We threw
Okay.
some ideas around.
So we'll talk about it at a different time.
Yes.
All right. Okay, next thing we have, guys, is the graphene. This is 4-6 stuff, all of the graphing that we were doing. So I'll give you guys kind of like a step-by-step. And this one, you guys will have a graph. There are very few, I think I have like 6 problems maybe on this test, because graphing covers a lot. Like giving you guys the graph, that's one of the problems. That takes up, like, first of all, a big bulk of your time, but I can also test you on max, min, increasing, decreasing, critical points. Like I can test you on a ton of stuff just by having you do one graph. So you will have one. Here is my recommended how-to, sort of. So find f prime. So find the first derivative, and then from that you get your critical points. Okay, so find f prime. From that you get your critical points. That's going to be part of your sign chart. Okay,
So within
probably
that
making
step-
a very strange noise.
So within that step, like, you do a sign chart?
So I would do the sign chart after this step,
Okay.
once you have the second derivative. So you find the second derivative. What's the, pretty much the same thing. Okay, so pips, good. We got our potential. I didn't even think of how to phrase that. You guys knew what I was asking. Okay, so f double prime gives us our potential inflection points. We haven't checked the sign chart, so we don't know for sure if they are in fact inflection points. Okay, so now this is where you set up your double sign chart. So set up a double sign chart. Remember, you're plugging the first set of test values into f prime, the second set of test values into f double prime, and then from that, so like once all is said and done, you take a look at your sign chart, you can identify your maxes, your mins, and your inflection points. Okay, so all of this is stuff that you guys had done so far. The new part in the graph is actually like plotting values on your chart. So like knowing what y values are important. So that's what comes next. So you identify, so these are all going to be your important x values. So you'll say like, oh, I have a max at x equals 3, and again at like x equals 7, and then identify your inflection points, your mins if you have any. And then the important part is that you take all of those x values and plug them into the original function. That way you have ordered pairs that you can start plotting. Okay, so plug these values, your max, your min, your inflection points, back into the original. To get ordered pairs. So then you'll have, 4, 5 ordered pairs that you can start to plot. Okay, so we've got some y values. You can plot those. Other important features, if they apply, asymptotes, intercepts, things like that. You can always find y-intercepts. Y-intercepts are super, super easy to find. Sometimes x-intercepts are easy. Sometimes they're not. Like if you got a weird cubic, x-intercept is probably not something you can find very easily. Asymptotes only apply if you've got rational functions. Okay, and then you've got 4 different shapes. So basically, once you have those points, you connect the dots using the appropriate shape. So if you look at your sign chart, you've got 4 possibilities. Plus plus, plus minus, minus plus, and minus minus. Okay, so the first sign is your first derivative. Second sign is your second derivative. So this means increasing and concave up. So that would look something like this. Picture like the right half of a normal parabola. Right? Increasing and concave down would look like that. Picture that as the left half of a downward parabola. Decreasing and concave up would be like the left half of an upward parabola. And then decreasing and concave down would be like the right half of a downward parabola. So don't memorize these different pieces. Just like picture the parabola that you're graphing. You know what increasing, decreasing looks like. If you're trying to do the concavity, just picture a parabola. So you guys can sketch out lots of little pictures. So then you just connect the dots using the appropriate shape. Like if you look at the sign chart and you notice it's a minus plus, connect the dots using this shape right here. And then everything will kind of fall into place. Good? Any questions on graphing? Yeah?
How do you know if it's supposed to be like above or below the x-axis when you're graphing?
That will normally kind of fall into place based on what points you have plotted so far. So like if you, are you thinking of like a rational?
I don't know. There were just some examples like in some of the homework we had, or like the classwork we had.
Okay. The polynomials, that should normally all be determined by like the y values that you plot in this step. So you'll have like some points will be above, some points will be below. If you're looking at like a rational, for instance, like let's say you were doing a rational and you had like you knew that you had, let's say, let's make an easy x-intercept and an easy y-intercept, and then you weren't sure if it was supposed to be like here and here versus here and here. You would just look at the shapes. Like let's say to the left of 0, you were supposed to have this shape. That shape couldn't possibly go down here because it would cross through the asymptote. So it must go right here. So you can kind of see like based on what shape you have, where it would actually fit.
Yeah.
And then same thing, like if you knew you're supposed to have this shape, it couldn't possibly fit in the upper left, so it must go in the lower left. You'll usually have like x-intercepts or y-intercepts to help you out too. You'll have enough that it'll be clear where it's going. Yeah?
Can you write the asymptote rules?
Oh yeah. Asymptotes, so for vertical asymptotes, you set the denominator equal to 0. And then for horizontal asymptotes, it all depends on the degree. So I'm going to use capital N and capital D for the degrees, just so I can shorthand a little bit. So we've got 3 scenarios. The numerator has a larger degree, they're equal, or the numerator has a smaller degree.
Both the asymptotes are ones that like fractions, right?
Yeah, the rational functions. Rational functions are the only ones that will have asymptotes.
Okay.
Okay, so if the numerator's degree is larger, this actually has no horizontal asymptote. Because the numerator will race off, it'll keep increasing. So this has no horizontal asymptote. You guys remember this one, equal degrees? It's the ratio of the leading coefficients. It's very fancy. So ratio of the leading coefficients. So that's, if you have an x squared in the numerator and you have a 3x squared in the denominator, it'd be 1/3. How about if the numerator has a smaller degree? 0. Good. So y equals 0 would be a horizontal asymptote there. Good. So if you have a rational function and only a rational function, look for the asymptotes. Okay, are we good so far? Okay, so I have one more thing I want to go over with you guys over the bullet points, and then I have that one that we left off of the 4-6 notes that I mentioned that we'd be doing today, and I think that's a really good like F prime example to do. So I just want to do one example of what you guys were doing yesterday. So we want to approximate the square root of 102. So this is yesterday's stuff. Just to kind of recap, make sure we're all on the same page. We're good. Okay, so if we wanted to approximate the square root of 102, you've got really 2 things that we need to start with. We need a function to use, and then we need like a starting value to use, our point of tangency. So what function could we use for this? Square root of x. Good. And then what would you use for our point of tangency? What's the closest thing we know? 100.
Well, I'll say the square root of 100.
Okay, so we need the y value to do a tangent line. So y value would be f of a, which is what? 10. Good. We plug 100 into the square root of x, we get 10. What else do we need? To get a tangent line, what else do we need? Slope. Okay, how do we find the slope? F prime. Good, so f prime. We can think of this as like x to the 1/2. So just do a simple power rule on it. So the 1/2 comes out front, and then power drops down to a negative 1/2. Okay, so we want the derivative at 100. So we've got 1/2, 100 to the negative 1/2, which comes out to be what?
1/20.
1/20, good. 100 to the negative 1/2 would be 1 over the square root of 100, which is 1/10. And then we multiply that by 1/2. Okay, so we've got all the pieces. Are you guys okay so far? Okay, so we're going to plug it into a tangent line. So first of all, let me kind of walk you through what we're trying to find, like why we found the slope, why we're doing a tangent line. So basically we're saying going from 100 to 102, that's 2 steps away, right? Like 100, 101, 102. So our change in x is 2, if that makes sense. Do you guys know how slope works? Like, I mean, just think algebra. Like slope is change in y over change in x. So this right here, this slope, we could think of it in 2 ways. You could think every time y goes up 1, x goes up 20. And that's how you guys would actually plot a slope, like back in Algebra 1. But what this means for us, change in y over change in x, this means every time x increases by 1, y increases by 1/20th. Does that make sense? So I'll say that again. Every time x increases by 1, y increases by 1/20th. So according to our estimation, that's our first ordered pair. That's our point of tangency. So if we wanted to go up 1, how much would our y value go up? 1/20th. So it would go up to 10 and 1/20th. And then if we wanted to go up 1 more, what would our y value go to? 10 and 1/10. Okay, so I am telling you right now, that's what the tangent line is going to give you. And once you see the tangent line all written out, you'll see that's what it actually gives us. So if we do y minus the y value, so for us, y minus 10 equals the slope, 1/20, and then times x minus 100. Okay, so remember the way we actually wrote this? We wrote a capital L linearization function, and then we moved the 10 over to the other side. Oops, moving the 1/20th, sorry, there's the 10. Okay, so these are all the pieces that I was talking about. X minus 100 represents the change in x. Whatever I plug in for 100, or I'm sorry, whatever I plug in for x, this will represent my change in x. Can you guys see that? Yes. And then I'm saying, all right, my starting point is 10, and I'm going to go up 1/20th for every change in x. Okay, so 1/20th times the change in x plus the original. Okay, so what we really have here, because this is, you guys have seen this written out for the slope before, right?
Yes.
Change in y over change in x. And then I said x minus 100 is really what? My change in x. So if I multiply slope times change in x, what am I left with?
Delta y.
Yeah, change in y. So once I multiply this out, that'll be my change in y, and then I add it to my original y. Does that make sense? Okay, so that's technically what we were doing yesterday. We were just kind of like plugging things into a tangent line and maybe not really thinking about what we were doing. So if I plug in 102, I get 1/20th times 102 minus 100, and then plus 10. So can you guys see that that does in fact give me 1 and 1/10? I'm sorry, 10 and 1/10. Or 10.1 if you're a decimal person. Maybe 101 over 10 if you're an improper fraction person. I don't know what kind of people you are. Okay. Are we okay with this? Good. Okay. So I want you guys to flip. It's page like 70. I'll find it. It was the problem that we left out of the notes in 4-6. Here it is. 77. It was this problem. I told you guys we'd do it as review because this is actually really, really good practice on some of the critical points, F prime, things like that. Okay, so we're on page 77. Okay, so if you look at that, it says let f prime equal 4x cubed minus 12x squared. So notice you're already given f prime. So this will give us lots of good practice. This time we're doing it with a function. You'll have to do it with a graph on your test. So first it says identify where the extrema of f occur. So knowing that we already have f prime in front of us, what can we look for? Set it equal to 0. Good. So we're going to take that first derivative, set it equal to 0. I'm going to factor it down so I can take out a 4x squared, and then I'm left with x minus 3. Okay, so where are my critical points?
0 and 3.
0 and 3. Good. Okay, since I'm telling you that we for sure have second derivative test, and we're going to need the second derivative eventually anyway, I'm going to show you, kind of run through how to do the second derivative test with this one. Okay, so first step to doing the second derivative test is finding the second derivative. So remember, this is already f prime. So what's f double prime?
12x squared.
12x squared.
Minus 24x.
Good, minus 24x. Okay, so how do we do the second derivative test again?
Plug in the CPs.
Yeah, plug the critical points into the second derivative, see what we get. All right, so plug those in. So f double prime of 0, we're going to plug that in. F double prime of 3. Okay, so what do we get if we plug 0 into the second derivative?
0.
0, so what does that mean?
Neither.
Neither. Good, technically it means the test is inconclusive, but I can tell you, if you see this, it will be neither.
If you got a 0 on a test, you fail, so
That's fair. That's fair. So I guess you could think of it as like failing to identify a
Yeah.
max or min, because
Yeah.
there isn't a max or min. There is neither. Okay, if we plug in 3, what do we get?
180.
We shouldn't get 180. We'd have 12 times 9, which is what, 108? And then minus 72,
Oh, mine, so I added it.
so 36. Okay, so we got 36, which means at that point, the second derivative is positive, which means it's a min. Okay, remember it's kind of counterintuitive. Concave up would look like this, so it would actually be a min. Okay, you guys good with that? Okay, so we could have done sign charts. Sign charts would have worked just fine for us. We're actually going to do a sign chart on the next part. So part B says find the intervals on which f is increasing and the intervals on which f is decreasing. So we're going to set up a sign chart using what function? An f prime sign chart. Good. By the way, especially when you guys are doing your graphs, when you're setting up those double sign charts, use your calculator. Remember when I walked around and showed you guys how to use your calculator, plug things in? You'd be wasting your time if you tried to do sign charts, like testing the values in the sign charts, I mean. Do those in your calculator. Okay, so this sign chart splits with 0 and 3. Okay, so use C right up here, how we've got like the factored version of our derivative. It's always easiest to plug things in there, especially because this, what can you tell me about 4x squared?
0.
Always positive. It's a beautiful thing. I don't really have to worry about plugging anything in there. This is always positive, so just worry about plugging something into my x minus 3. Okay, so if I plug in something negative into x minus 3, it comes out negative. Okay, if I plug in like 1 or 2 or something like that, negative. Okay, so we were correct in saying that this is neither max nor min. That's good news. And then if I plug in something bigger than 3, positive. So we were also correct in saying this was a min. All right, so I know first derivative test probably would have been more convenient in this case, but I was just showing you how the second derivative test works. Okay, so let's start with increasing. Where is my function increasing? 3 to infinity, good. And then if you were to give an AP explanation, which you will have to tomorrow, you would say because
Because it's.
Not increasing. F prime is positive there. Good. Okay, now decreasing. Be careful with decreasing.
Wait, I have a dumb question about the explanation.
Mm-hmm.
So, could, like, see how on the side of it you just wrote like F prime? Would I have to write like F prime of X, or do I have to?
Oh no, F prime is totally fine.
Okay.
And that's just because our independent variable hasn't changed. We've always been
Okay.
using an X. So yeah, you don't need that. Okay, decreasing. Anyone see what I'm talking about when I say be careful?
Everywhere but 0.
Everywhere but 0. Well, not everywhere.
Well, but up to 3.
Up to 3. Okay.
So you do the U for this one, right?
Yes. So you'd write from negative infinity to 0. And then from 0 to 3. Because our function is not decreasing at 0. Our function is stopped at 0. Momentarily, but it's stopped at 0. So we have to disclude that from our interval. Does that make sense?
Yeah.
We good. So make sure you do that. It's a critical point, which means your graph is stopped there.
Will that happen to all of your critical points? Like they won't count?
So yes, I mean, that's why we make open intervals. So the critical points, at the critical points, your function is neither giraffes, your function is neither increasing nor decreasing. So yeah, you disclude whatever they are. That's why we have open intervals. Come
Okay, I like that.
Yeah.
I'm good with that. Girl.
No.
Okay, question, Casey?
How come we didn't have to find the potential inflection?
Oh, we're getting there. Because we've been asked about extrema and we've been asked about increasing, decreasing. We really haven't needed to bring the second derivative in yet. We brought the second derivative in so that we could test the critical points.
So extrema is just the first
Extrema is just first derivative. Yeah, that's testing whether your critical points turn out to be max, min, or neither. So we could have done all of this work without even touching the second derivative. I was just showing you how the second derivative works because you're going to have to use it tomorrow. Okay, so now we get into concavity. What does concavity have to do with? Second derivative. Okay, so we already have our second derivative, which was nice. We're just going to set a sign chart up for it. I don't know. Like a sign chup. Like I think I was ready to say up, like set a sign chart up, and I think they just all blurred in together.
Video is so interesting.
Oh, they're going to love it. Oh, all right, so there's our second derivative.
Wait.
Right? Question.
Okay, so what I'm seeing is that for A, did we do two methods?
We only did the one method. Finding your critical points is always the same. There's no second way to find critical points. You take the derivative and you set it equal to 0. And then once you have your critical points, you can do one of two things. This kind of demonstrates the first derivative test, setting up a sign chart and showing like, oh, this was no change. This was a change that denotes a min.
Yeah.
Or if you're doing the second derivative test, you plug your critical points into the second derivative.
Are we gonna have to are you gonna make us do both of them?
Yes. So not on the same question. You'll have to do first derivative test at some point. You'll have to do second derivative test at some point.
Okay.
Okay, so we've got our second derivative. We're going to set that equal to 0. So let's factor 12x. Okay, what are our pips? 0 and 2.
I love that word.
Okay, so now we're labeling our sign chart. That way we know that we're actually plugging things back into the second derivative. Use the factored form. It's probably easier. So we plug in something negative. What do I get? Something positive, good, because this would be negative and this would be negative. So I get something positive. Between 0 and 2? Negative, because this would now be positive, but my x minus 2 would be negative. And bigger than 2? Positive times positive. Good. Okay, so to answer that first question, where is f concave up? Negative infinity to 0. And 2 to infinity. Good. And your AP explanation? Because f double prime, no it's, because f double prime is positive there. Concave down?
0 to 2.
0 to 2, because?
F double prime is negative.
Good, because f double prime is negative there. Okay, so now sketching a possible graph. The reason this says possible is because we don't actually have any y values. And that's because we don't know what f is. We could probably work our way backwards and talk about antiderivatives, but something for a later day. So let me set up a quick double sign chart just to line them both up, use all the transition points. So we've got 0, 2, 3. Those are all our transition points. So we're just going to transfer the sign charts down. So f prime is negative to the left of 3 and positive to the right. And then f double prime is negative between 0 and 2, and then positive everywhere else. Okay, so again, the reason that this says sketch a possible graph is just because we don't really have enough information to make it perfect yet. Like, we don't know what the y values are, but we do have enough information to get the general shapes. So set up, we've got 1, 2, 3, and 0. So let's just say, just to make this easy, that our graph goes through the origin, because it could really have any y-intercept. We don't actually know. So let's just say that it goes through the origin. So we start with negative, positive. So remember, negative, positive would be decreasing and concave up. So you can always kind of look back at those little shapes that you've got. So I wrote our shapes right, let me see, right here. So it's got to be this shape. Okay, so it's the left of 0, it's going to be that shape. So we can just, like the left half of a parabola, just have it finish off at the origin right there. All right, so it could look something like that. Then from 0 to 2, our graph is what and what? Okay, so what does that mean? Decreasing, concave down. So what's changing at the origin? Inflection. Inflection changes at the origin. So this is now changing to this shape. Okay, so now it goes kind of like that. It's like it's concave down until 2. And then what changes at 2? Yeah, now it's concave up. Concavity changes again. So we're going to keep on decreasing, but now we've got a point of inflection, so now it's back to being like a right side up parabola. Okay, so some strange things are happening here so far. It's just like wiggling down like this. Then what changes at 3? Now it goes up. Good, so we'll try to make this smooth like that.
Yeah, I feel like mine is.
Try to make it smooth.
Try to make it smooth. It's not going well. So something like that. All right, and again, we don't know like how far it actually went down here. We don't know what the y-intercept is. We've got the general shapes. Okay, so we got 4 more minutes. Does anyone have any like quick questions? Was there anything you guys wanted to go over? I will tell you right now, those review problems that I have on the sheet, I do have a video going through all of those review problems. I have next hour off, so I will post those and I'll work on posting this. Sorry, Latin people, for what happened here today. Question?
Unit circle.
Learning the unit circle. That hand trick would be a good thing to go off of. And I mean, really just like memorize. If you can memorize the first quadrant, especially like the 0, the pi over 2, like picture where those are. Guys, we had a unit circle question. So here's a couple features that would be really good to know, is knowing that x always goes with cosine and y always goes with sine. So these four you guys should know very quickly. All right, so like these 4, guys, stay with me for a second. So this is 0, 0. If you go 1 unit over, that would make the cosine 1, but the sine is still 0 because you went 1 x value over. Up here, guys, if you go up 1 unit, that would be up a y value. So this would make the cosine 0 and the sine 1. That's at pi over 2. Over at pi, your x value would be -1, so that's cosine. Sine is back to being 0. Down at 3 pi over 2, sine is -1, because that's y. Cosine would be 0. And then really, if you memorize the first quadrant, you should be able to kind of transfer it anywhere around. So at pi over 6, for instance, pi over 6, pi over 4. Have you guys ever seen these charts before, like the cosine?
No.
Cosine, sine. There's so many different unit circle things.